All right, so what I'm going to be talking about is then the proponent rule for how to calculate the ground motions from using the GMPEs for splay rupture cases. Okay, Norm talked about this morning, so I won't spend too much time here, but basically we've evaluated 4 different methods for using the GMPEs to compute ground motions for splay ruptures. And the first method is SRSSing ground motions computed from both the primary rupture and the splay rupture. And Jeff called it secondary. I keep calling it splay. So we're going to have splay as the secondary rupture, but compute them individually. So you have basically 2 fault sources. You have your primary fault source, and you have your splay fault source. You use the GMPEs, and then you SRSS the 2 resulting response spectra. Method 2 is using an average of the parameters based on the area of each respective fault. So your magnitude would be what you would compute from the total area of the full splay rupture case, and your fault parameters such as rake, dip, and width would be based on the average then of the area. Okay. Method 3 is similar to method 2, but we are using fault parameters averaged then by a distance metric. So the magnitude is the total magnitude for the full splay rupture, and then we've discretized the fault sources, and we've used a weighted average based on the distance from the respective fault plane. So this is for dip. We've done the same for dip, for rake, and also for the width. And then the response spectrum is computed using the distance metrics to the closest point. In method 4, we simply, the magnitude is computed from the full fault area, the full splay rupture, and we simply use the parameters in the GMPE from the closest point. So we use the distance metrics to the closest point. We use the dip, the rake, and the width of the closest point. In method 5, we have our simulations. So as Jeff just described, we compute the simulations for the primary and the secondary rupture using the broadband platform. We combine the synthetics in the time domain, and from that we compute the ROT-D50 response spectra and the ROT-D50 spectra. Okay, so what we're trying to do is we're trying to use the simulations to guide us in which methodology we should use for the GMPEs to compute the ground motions for the splay rupture. So the first step in this is we're using the simulation results. So we're going to assume that the simulation results are correct. That's the right answer. So we create simulations for the splay rupture case, and we do that as Jeff discussed for the full splay rupture. That's step 1. Then we compute the simulation results for the primary segment by itself. That's step 2. So in this picture, that would be just the Hosgry segment. Then we compute a ratio. So the numerator would be the ROT-D50 spectra for the full splay rupture. The denominator would be the ROT-D50 spectra for the Hosgry results by themselves, and then we get factors. And we're going to do this then for each of the 4 different GMPE methods. We're going to go through, and the numerator would be whatever the method prescribes for what the full splay rupture would be, and the denominator is just the primary segment. And we're going to compute factors for each of the 4 GMPEs. And then we're going to compare the factors that we get from the GMPEs with the factors that we get from the simulated results. And we're going to use those simulation factors to guide us in choosing the most appropriate method for using the GMPEs. Okay, so this is the first case that Jeff went over. So the primary rupture is the Hosgry fault. It's a vertical strike slip fault. The secondary rupture is the shoreline fault. It's also a vertical strike slip fault. So for method 1, we're SRSSing We're treating the Hosgri and the shoreline like two separate events, and we're SRSSing the resulting ROT50 spectrum. So we're just combining them. This is not a pointer. This is just we're combining them, these two, SRSSing these two. Then method 2, this shows the parameters that we put into the GMPE for method 2, which is a weighted average by area on the dip, the rake, and the width. Method 3 is a weighted average then by the distance on the dip, the rake, and the width. And method 4 is just using the dip, rake, and width of the closest point. And as you can see for this case, when you have two vertical strike slip faults, methods 2, 3, and 4 are nearly identical. Okay, so this figure shows then how the simulations compare with each of the different GMPEs for those 4 different methods. So here we have the results of the GMPEs in gray for method 1. We have the results of the GMPEs using method 2 in this plot. This is method 3, and this is method 4. When I show the factors, it will become much more obvious, but the gray lines in this plot, and this plot are essentially identical. The simulations are closer to the GMPEs for method 1 than they are for the other plots. And then we notice the same features that Jeff just pointed out. So that at high frequency, Jeff worked in period, I'm in frequency, so I'm flipping it. But at high frequency, we're seeing then that the X-sim is very high. It's almost a factor of 2 above the Graves and Pitarca, and SDSU is somewhere in between. And then at the low frequencies, it's much lower than the Graves and Pitarca and SDSU, which are the same for the low frequencies, which is what is expected. Okay, so in these figures, I'm showing then this is the plot. This is method 1, because cat's out of the bag. We're going to end up saying that SRSS is the approach to use. So this is the SRSS, the GMPs for the SRSS compared with the simulations. In these plots here, the solid line for, this is Graves and Pitarca, SDSU, and XSIM. The solid lines are the numerator of the ratio, and the dotted lines, that's what we're using as the denominator in the ratio. So you can see then how the factors are computed. And so these are just this is the ratio in natural log units here. So for low frequency, here we have 3 methods agreeing pretty well. The factors for the 3 methods agree pretty well. SDSU and XSIM, or SDSU and Graves and Pitarca agree fairly well, really well at the high frequencies, and then XSIM is very high. And part of this is due to the higher ground motions computed for the splay case, but also XSIM generates lower ground motions for the primary segment by itself. Okay, so this is these are the plots for method 1. On these plots, what I'm showing here, this dotted gray line here is XSIM from the previous slide, the simulated XSIM results. Graves and Pitarca is the solid line through here, and XSIM is the dashed line down here, like a dot dash. And in general, all 3 methods agree with the factors. All 3 simulation methods agree with the factors computed using method 1.
Katie, which one was XSIM? Wasn't that the top one?
XSIM is up here. Did I misspeak? And then
that's SDSU. Is on the bottom.
SDSU is on the bottom. Sorry. Once I PDF it, this is supposed to be a dash dot line, but I guess the PDF changed it to just a dashed line. But XSIM is at the top. So all 3 of the simulation methods, the factors compare very well with the factors that are computed using the SRSS technique for then the low frequency. And at the high frequency, there's good agreement with the simulations for Graves and Pitarca and SDSU. And we also get a little bump here at 10 hertz. This is the strike slip case. It's going to be, you'll see that when I show the reverse case, it's going to become more pronounced. And then this shows the comparison with method 2. Method 2, 3, and 4 are very similar, so I'm going to flip through them. The only thing that's going to change when I flip from method 2 to method 3 to method 4 is the Campbell and Buzornia. So if you look at these red points here, they'll change. And the reason why Campbell and Buzornia is affected by this is that this is really the only method that is sensitive to the width parameter, because they specify a hypocentral location instead of, that's what they use, the detour. So then you see the red change in method 2 to 3. And then between method 3 and 4, the width is so similar that it's not sensitive to that change. And this is just showing the comparison then between the simulations here and the 4 different methods: method 1, method 2, method 3, and method 4.
Those points on the right are the same as the lines on the left. That's right.
These points, yes, these points correspond then with the lines in these figures here. I'm hoping it's clear up there.
And your conclusion here was, again, method 1 was closest to the simulation.
Yep. Okay, so this was for the strike slip case. And now I'm going to show you the results for the reverse case. So this large fault here is the primary Los Osos fault. And then the secondary San Luis Bay fault is the smaller one here. And this is Diablo Canyon. And then these are the inputs that were used in the GMPEs for method 1, SRSSing these top 2 cases, method 2, method 3, and method 4. So now we're seeing some changes in the dip. The rake isn't going to change because it's 90 for both of the faults, and then larger changes than in the down dip width. Okay, just like before, so these are the simulation results compared against the GMPEs for method 1, method 2, method 3, and method 4. We get better agreement between the simulation results in method 1 GMPEs than we do for methods 2, 3, and 4. Also, the difference between the XSIM and the Graves and Pitarca at the high frequency is not as large for this reverse case. And the SDSU simulations end up agreeing better with the XSIM as well for this case. Okay, so these again show the numerator and denominator that we used in our ratio for Graves and Pitarca, SDSU, and XSIM, and the factors computed from those. And so in each of the following plots, I'm going to then show the simulation results in the same way. So XSIM is the large this dashed line up here. Graves and Pitarca is the solid, and this is SDSU, and that bump at 10 hertz becomes more pronounced. And actually, I'm going to back up. I think why we're getting that bump at 10 hertz is when you compute the rupture for this splay case, it seems like this peak is shifting to higher frequency for that combined rupture, and that's not happening in the denominator. So I think you're getting a larger difference at 10 hertz when we compute the factors there. I'm also showing only 6 GMPEs and not all 9, and that's because Bindi, Idris, and Zal don't have a hanging wall factor, so I'm not showing those. So then these are the GMPEs for method 1, and then the factors. And again, the factors at the low frequencies are comparing pretty well with the simulations, and then at higher frequencies, they're comparing better with SDSU and Graves and Pitarca, with the exception of this bump here.
Do we know why that 10 hertz bump is there, Kim? He's shaking his head no right now. one thing we need to look into a little bit on that.
Okay. And then quickly I'll go through 2, 3, and 4. This is method 2, method 3, and method 4. Okay, just to show them all in one plot, the conclusion here would be for this geometry as well, SRSS seems to be doing a better job of, well, reproducing the simulation results, or seems to be more consistent with the simulation results. Okay, now I just want to show you a comparison because we ran different magnitude scenarios. So the results I just showed were using the large magnitude cases, and the reason we presented the large magnitude cases is it's more likely to get rupture to go onto a splay when you have a larger magnitude rupture on your primary fault. But we did run other magnitude cases. So in this particular case, we had a magnitude 7.2 on the Hosgry fault. This is the magnitude 7.4, which I just showed. And what's interesting here is you see a larger difference between XSIM and both SDSU and Graves and Tatarka for the high frequencies when you have a smaller magnitude on the Hosgry fault. And then for magnitude 7.4 on the Hosgry fault, you see less of a difference between XSIM and Graves and Tatarka, and even less of a difference between XSIM and SDSU. So SDSU seems to be pretty sensitive to just a small change in magnitude here. Here's a comparison of the factors computed for the 7.2 case with the simulations for the 7.2 case, and the factors computed for the 7.4 case and the 7.2 case. And the factors, the resulting factors are almost identical, so no difference really between the two magnitude cases. And this is showing the same thing for the Los Osos and San Luis Bay case. So here we have a magnitude 7 on the Los Osos, magnitude 7.2, and a magnitude 7.4. In all these cases, XSIM agrees better with the other two methods. In some cases, it's about the same as SDSU, the high frequency. And then this just shows the factors. So really the only difference between the factors from the smaller magnitude case to the larger magnitude case is the Chu and Young's model. Seems to be more sensitive or has a stronger hanging wall effect. So these are the conclusions. A lot of them are the same as the conclusions Jeff had. But at low frequency, all three of the simulation, well, the factors for the SRSS method agree with all three of the simulation methods. And at higher frequencies, the factors from the SRSS method are more consistent with SDSU and Graves and Tatarka. There is that bump at 10 hertz for SDSU, which you need to learn more about. There's a large, XSIM is much larger at high frequencies, especially for the strike slip case. This is what's expected from the model because the GMPs have a stronger saturation than the XSIM model. That contributes to the large factors. Let's see. So overall, I would say that for the geometries that we looked at and for the site location of Diablo Canyon, the proponent model would be to use the SRSS method to compute ground motions for this light case.
Thanks, Katie. Questions for either Katie or Jeff, clarifying what they're trying to do? Again, we need to find some way to make the GMPs work for these cases. Well,
Katie and maybe Jeff, do you know why when the XSIM was run, that it appears that certainly on the splay fault, in timing, it's very different from, let's say, Graves, Tatarka, SDSU. When I looked at the time series, they look like they're much more separated in time, whereas SDSU and Graves and Tatarka seemed like they had very good overlap between in the time series when the splay fault and when the Hosgry were interfering. but it looked like XSIM was two separate earthquakes. In other words, it was, if you added them together in time, they would not add together in the same way.
I think those figures are in your presentation, Jeff. But doesn't XSIM has a shorter duration, right? I don't know where it is.
Yeah. I don't know about the duration, if it's shorter or not. But I noticed that too, Ralph. And I looked to make sure there wasn't a problem, actually, because I was concerned. But so I don't know the answer, but I know that it's there for some reason.
Did you put in a propagation delay? That time lag is the time when the primary rupture gets to the point of the splay. But XSIM doesn't have Green's function, so it doesn't actually compute arrival times. So maybe that has something to do with it. But you have to also account for the difference in wave propagation from the two faults. There's another time component possibly.
If you look at this plot, the San Diego model has a pretty short duration, right, compared to the next one, XSIM. Those don't look so different, Ralph. Go to the Grayson Katarka.
Okay. I flip one more and go one more. Okay. Now, so the time here, I can't exactly see, but it looks like it starts at 45. Is that just an arbitrary?
XSIM is shifted, and I don't know why. They've had it, I guess. Yeah.
Okay, and is the total duration that's plotted here is 50 seconds. So that's constant in all these plots. We're looking at the same time scale? Yeah, 50 seconds. Okay, so that time lag, it's 9.5 seconds, about 10 seconds. I mean, I guess that kind of makes sense. One thing I'm actually not sure about. This is a specific realization with a specific hypocenter. Does that time lag change, or I can't recall. Were you doing multiple hypocenters? Yes. Okay, and so that time lag would be dependent on where the hypocenter is relative to the splay. Yeah, different for every realization.
Did you put up something so you guys could see seismograms and understand how things were being added?
Yeah, it confused us. Katie, could you flip back one? I just want to.
You want your method?
Well, yeah, so that looks like, yeah, I mean, this looks like pretty close. Yeah. So one's closer than the other too, right? So there's a time lag, but they're also not located in the same place. Time lag, but there's also the distance from the hypocenter of the secondary segment is closer than the hypocenter of the primary segment. Right, so there's a time lag between when the first hypocenter travels to the second hypocenter, and then there's a separate lag between, the start of shaking from that second hypocenter.
Yeah.
Right, and the energy coming from the first rupture is not traveling along the fault. So in this case, the Hosgri is actually, it doesn't come right to the site. So it's not necessarily, yeah, I guess it's fairly close. Yeah, I'm not sure if we're getting to the bottom of this route.
A quick question. Jeff, related to the text I sent you, have you guys filtered those motions at all once you added them up?
No.
Okay, so because some of them, maybe I'm wrong, but in velocity they look like they have a uniform pulse in one direction. And if you integrate the displacement, are these still baselines correct? So that was a question I asked privately by text, but I was wondering maybe you filtered those or not. So you might have a residual displacement on those.
I don't know, Rob. Does your method? I mean, your method combines the waveforms from the different subfaults. Do you do a filter?
Well, there's no filtering, but yeah. So this is velocity, and in particular, the middle trace there, which is the shoreline, which goes right by the site. You integrate that up, you're going to get a static, which is what it should be. So this,
so did you guys
well, it would be the long periods using the same Green's function. So there's no filter at, there's no band limitation at the low frequencies, if that's what you're asking.
But I guess the question to Swift is that when you combine those time series, you can create those bumps that were not there. Was that intended, and do you want to leave them there, or is that something you need to filter out or baseline correct? Maybe you don't care.
Well,
I don't know.
it should be linear superposition should be fine.
The way we're going to use them is in the GMPEs for SS. Yeah. SRSSing them, right? So we're going to get a smooth model out. So that's just the response spectral values. So we're not going to actually use these. This was just to gauge which one of those methods is appropriate or the best way for us to simplify the problem.